Institute Colloquium. Today we're very happy to have Barbara König talking to us about behavioral metrics via functor lifting. So please, Barbara, whenever you're ready.
Okay, so thanks a lot for the introduction, and thanks a lot for inviting me, giving me the opportunity to do this talk. And yes, so the topic of the talk is behavioral metrics via functor lifting, a coalgebraic approach. You can see that there is quite a long list of co-authors that I'm listing here. And so this has actually been work that has been going on for a while. And so that's why this is based on quite a lot of papers and also quite a lot of co-authors. So I'm happy to take any clarifying questions. So if you have any questions during the talk, please feel free to ask me, especially if there's something that I should maybe clarify or restate in some way. Okay, so what's the overview of this talk? So I'll start with a bit of a motivation about behavioral equivalences and metrics. So these are the items that we study in this talk, and I mean the idea is to understand what they are and why we are actually interested in them. And then I'll do two concrete examples, which are metric transition systems and probabilistic transition systems. What I'm always telling my PhD student is, before you generalize something, you have to have at least two examples, two things you want to generalize. And so these are my two motivating examples, which I tell to you, and then we will generalize from there. So the first half of my talk will be largely category 3, and then we're getting into more categorical things. So I'll talk a bit about Coalgebra as a general framework for transition systems, and then how to handle these behavioral metrics, which are my main research interest in this setting of coalgebras. And then we'll conclude with some compositionality result up to techniques, so some bit more advanced stuff. But feel free to ask questions. I mean, I can also skip the last chapter if there's more interest in the first part, and then I will adapt accordingly. Okay, so let me first maybe say a bit more about my background. So I'm a computer scientist, so I studied computer science, and my main interest, or what is dear to my heart, is actually system verification. So you're given a system and you want to verify it. You want to compare it with the specification. You want to know whether the system is working correctly. You want to derive some information about the system so that you're more confident that it is working correctly. And for this, I like to use categorical methods because very often it's a bit cumbersome if you have some kind of system type. And then you design some analysis or verification procedure, and then you get a new system type, and you have to design another procedure, but it's kind of looking awfully similar, right? And then you do the same thing again and again and again. So my idea is always to do things generically so that they work for large classes of system, and not for each type of system you have to restart and design another procedure. And that's typically my motivation to use category theory. I'm not a category theorist, but I like to use it for this purpose. And the topic I want to talk about today is analysis of state-based systems. And so I'll show some example on the next slides, but assume that you have a system that consists of states and there are transitions between states. So this is the favorite way of modeling systems of computer scientists. You want to analyze it. And what we're in particular interested in is to compute behavioral equivalences. So we want to say things like, oh, there's this state and there's this state, and they behave the same from some point of view. And why is this good? Why do you want to know this? Well, there are a couple of reasons for this. You might want to compare a system with a specification. You might minimize the system by merging states that have the same behavior. You want to, for instance, to analyze model transformation. You can also do this using behavioral equivalence. And also verification of cryptographic protocols is sometimes based on this notion. So you have two protocols and you want to know whether they're equivalent from the point of view of an external observer, and the external observer is the attacker who wants to figure out whether there is some knowledge that can be obtained from interacting with the protocol. So in this talk, the I'm actually not much talking about behavioral equivalences. I'm much more interested in behavioral metrics. But let's start maybe with behavioral equivalences. And first, we'll start with the notion of bisimilarity. That's a well-known notion in the theory of concurrent systems. And so you assume you have some set of labels. You have a set of states that are called typically X. And there is a transition relation. And the transitions go like from a state X with label A, you can go to state X prime as in an automaton.
So that first S should be an X, or
the first S should be an X. Yes, right, exactly. Yeah. Okay, and then what is a bisimulation? It's just a relation on the state space that has the following property. If there is a pair in the relation and you have a transition from X to some other state X prime, then the other state to which it is related must also be able to do an A transition and go to some X Y prime such that the two resulting states are related. So each transition from X via A to X prime can be mimicked on the other side by a transition from Y to Y prime. And actually also vice versa, this is handled in this way by saying that this relation must be symmetric. So also each transition of Y can be mimicked by a transition of X. And then if you have a relation, then a pair of states is called bisimilar if it is contained in the relation, which basically means that forever the transitions of one state can also be mimicked by the transitions of another state. So there's a very nice characterization of this as a two-player game. So I really like these game characterizations for these behavioral equivalences. We have often worked with them. And so you have a state-based system. So maybe I can here show the state-based systems. It's just a couple of states and label transitions. And you want to compare these states X and Y. You put two tokens on the states. And the player one, who is the attacker, now chooses one of the tokens and makes a move with an A transition, either to 2 or 3 or to 5 or 6. So the attacker can move from both states. And then it's the defender's job to answer from the other state and also make an A transition. And then you end up in another pair of states, and then the game goes on from there. And then the attacker can again choose which token to take, makes a move, the other has to answer. And so if player 2 cannot answer, player 1, the attacker wins. And if the game goes on forever, or if there's always an answering move for the second player, then the second player, the defender, wins. And the defender has a winning strategy if and only if the two states are bisimilar. So this is just an alternative characterization of what we've seen before. So maybe let's try a bit of interactivity. So I hope that the rules of the game are clear. We play on this arena, so on this transition system. And actually, I can tell you that the two states are not bisimilar. So if you're an attacker, you are able to win. You should be able to make some moves that I cannot mimic. I'll play the defender. So any moves that you would like to take. So you can choose either to go from X to 2 or 3 with an A. You can choose from Y to go to 5 or 6 with an A. And I have to mimic this from the other state. What would you like to do?
I think I'm not clear on which are the two states. You said I can move.
We start with the states that have these red tokens. I hope you can
Right.
see 2 red tokens. That's where we are currently. And then you can take either one of these states and make a move to one of the successor states, the one that you can reach with the arrows.
okay. So can we move to 3? Oh, sorry, Kevin.
Sorry, and then what determines what's a valid answer for player 2?
Oh, I should do a move with the same label. Otherwise I can do everything, but it has to be the same label. Yeah. I can answer with the same label.
Yeah.
Okay, I moved to state 3.
You move to state 3. Okay, you move from 1 to 3 with an A. So I have to answer with the same label. And I move from 4 to 5. We're now in 3 and 5. Okay. So it's your turn again, and you have to make a move.
Oh, I lose, don't I?
Ah, no, you will win.
I will
because
win. Okay.
you can actually, the attacker can change states. So it
Oh, I
is,
can become 5?
and,
No.
and each round you can decide on which side to move.
Okay, and then on from your state 5, I'll move to C, please.
Yeah. From 5 you do a
Right.
C, and then I'm lost. I'm in 3 now, and I cannot do a C. So you win, I lose, and actually I could not have played any better. So you have a winning strategy, and that actually means that the two states X and Y are not bisimilar because there's a winning strategy for the attacker, which means they have, from a computer science point of view, they have different behavior, and we want to consider them as different. So they're distinguishable from the observer who interacts with the system and plays this kind of game. And there are many instances where this is interesting and important to figure out which states are bisimilar and which not. So that was a bit the start, but then now we want to go one step further and say, okay, I'm not so much interested in behavioral equivalences. I'm rather interested in so-called behavioral metrics. So this is a quantitative notion of behavioral equivalence. So we don't exist on the exact same behavior. They don't have to do exactly the same, but we measure somehow the distance. Usually there's, and you will see now some quantitative information. Now it's not just labels, but numbers on the transitions or on the states. And then we want to say something, okay, these two states, they have fairly similar behavior, but it's not quite the same. It differs up to some small epsilon or so, for instance. That's the idea I want to say. Because in reality, systems with quantitative information, you really rarely have two states with exactly the same behavior, but maybe you have states with similar behavior. And this is this area of behavioral metrics that quite a few people are now also working on. So I think you know what a metric is. Just to say, I'm working actually with pseudometrics. I just require that the distance of x and x is 0, but not necessarily that if the distance of something is 0, then it is the same, because things could be different yet have distance 0 because they have simply the same behavior. Otherwise, we have symmetry and triangle inequality. We have pseudometric spaces, sets equipped with a metric. And what will also play a role is the notion of non-expansive functions. So a non-expansive function is just a function that after applying the function to the parameters, you get a smaller distance. So the distance on y after applying f to x and y is smaller or equal than their original distance on x. We could in principle do everything for not just for the reals, but for quantals, so more generic structures, but I'll stay with real numbers or mapping to the interval 0, 1 here. Okay, so then let's come to the first example for which we want to define a behavioral metric. This is the notion of so-called metric transition systems that stems from a paper by De Alfaro et al. I simplified it a bit. So you have given a metric space. So a metric transition system is a tuple consisting of a set of states. So it's again a state-based system. You have a transition relation. The transition relation is unlabeled. It's just pairs of states. And to every state, you assign an element of M. So each state in this case is now labeled with something that is an element of a metric space. So this is such a transition system. I have 6 states and I have transitions, and each state is labeled with an element of a metric space. In this case, it's just the interval 0, 1 with Euclidean metric. So you just measure the distance of the two things. And now the question that people ask is there a reasonable way to define what the distance of 1 and 4 is? If you just leave away the blue numbers, their distance is 0. I mean, they're behavioral equivalent, but the numbers in the successors are a bit different, so they're not quite behaviorally equivalent. I mean, you want to measure somehow how they differ. There are several ways to do this, but the most common people agree that somehow the Hausdorff metric should play a role here in measuring this distance. Why should it play a role? So basically, the idea is you take a bit of a co-inductive view and say, like, if I could measure the distance of my successors, then I have a distance on X or on the successors. And now, but I have sets of successors. And now the question is, if I have a distance on the base set, how can I lift it to a distance on sets? And one of the most well-known ways to do this, lifting a distance on some set X to a distance on subsets of X, is the so-called Hausdorff metric. And the Hausdorff metric does the following. So it takes two sets over which we have a metric, and it defines a metric on top of it. It says, okay, for each element of X1, please give me the closest element in of X2, and then I take the maximum over all these minimal distances. Same other way around, and then I take the maximum. So for each element in either in X1 or X2, you take the closest element in the other set, and then the maximum of all the distances that you get. And okay, let's do this with an example. So these are these two sets. So for each element, so these are the black dots here, you take the closest element in the other set, so I kind of roughly set where the closest neighbor in the other set is. And then you take the maximum, so probably the maximum somewhere here. That's the element that has, if it has to travel into the other set, it has the maximal distance to travel into this other set. Okay, so once I do this, I know how to do the lifting. I can set up a fixed point equation for my behavioral distance. So the fixed point equation for the behavioral distance is, if I want to measure the distance of X and Y, well, I first take the labels of X and Y and measure their distance, because I mean, the distance should at least be as large as the distance between the two labels. Then I take here, these are the sets of successors. I take the sets of successors, and then I take the Hausdorff distance over the set of successors. This is a fixed point equation. Why is it a fixed point equation? Because the unknown is D, and it occurs here, and it also occurs here on the other side. Do you see my mouse actually? Yeah, okay, good. You also see it on the other side, and then you do the Hausdorff listing. So it's a fixed point equation where D is the parameter. And what you want is the least fixed point, the smallest fixed point for this fixed point equation in the order of the reals. And so this transition system could be cyclic, so this is not completely straightforward to solve this fixed point equation. So let's do this example. So you have the distance between the successor states. This is now marked in green. So for instance, the distance between 3 and 5 is 0.2, and because that's just the difference of 0.7 and 0.5. And so I assume they don't have any successors. That's only, they will measure the distance only over this label. And then you compute the Hausdorff distance between 2, 3 and 5, 6 based on the underlying distance. And what is the poor state that has the farthest to travel into the other set? Yeah, that's actually 6, because 6 has to go here and it takes its distance 0.3, and all others have a shorter path actually to travel into the other set. For instance, 5 needs only 0.1 to go there, and so on. So then the Hausdorff distance here is 0.3. This is the maximum of all these distances, or the min-max, if you take the min-max. And so then you take the maximum with 0, which is the distance between these two elements, and you get 0.3. So from the point of view of metric transition system, this is the distance between these two states. Okay, this is the first example. So now the question is, well, do we have a second example so that we can actually generalize something? And the second one is probabilistic transition systems. So I have transition systems with states, and the transitions are now probabilistic, so you have probabilistic branching. So again, you have a set of states, which is X. You have a set of terminal states, which is a subset. And to each state, you assign a probability distribution over the successors. So basically say, oh, from this state to this state, I get with probability 0.5 or something. And so this is an example. So for instance, you have these states 1 and 2, and 2 goes to 3 and 4 with probability 1/2, and 3 and 4 are clearly different. One is terminal. Terminal states are marked by this double circle, and the other is not. And the other is kind of doing the same thing, but deviating by some small epsilon. And now the question is, what do we want to be the distance of 1 and 2? And the theory, okay, should somehow say, okay, the distance of 1 and 2 are epsilon because they really behave similarly, have similar transitions, but they differ up to some small epsilon. Okay, and how do we do this here? I mean, same story, you do a fixed point computation. And so this time the metric is defined like this. The distance is 1 if one state is terminal and the other is not. It's 0 if they're both terminal. And otherwise, you take the distance on probability distribution. You don't want to take distance of sets. You take distances of probability distributions this time. What's the standard way of lifting a metric on a set to a lifting on probability distributions over the set? Well, people will usually tell you that this is the so-called Wasserstein or Kantorovich metric. That is actually the solution of a transport plan. So you have, think of this. This is our underlying state set. It's 3 states, A, B, C. Think of them as some kind of cities or places where things are manufactured and consumed. And so you have some kind of supply, Px. This is the first distribution to which you want to define a distance, is this here. So here you manufacture a quantity of 1, and these 2 manufacture nothing. And Py, this is what you consume. So this state A consumes nothing, and the other 2 both consume 1/2. And then there's a distance between these 2 states. And then the question is, what is the best transport plan to transport your goods from the supply to the demand based on the underlying distance? So transporting a unit from A to B basically costs me 1/2. And then, okay, there's not much choice here. What you do is you just transport 1/2 from A to B and 1/2 from A to C. And then you compute the overall cost, and it is 3/4. And there's actually a dual notion to this. And this is because there are 2 dual characterizations of lifting. And the other one has also a nice intuitive explanation. The basically idea is you now hire a transport firm to do the transportation for you. And you set a price at the locations. And you buy for this price at every location. So your transport firm basically buys for this price and sells for this price at the other location. And the firm wants to maximize its profit. So it wants to sell, of course, for more than what it buys for. But the price function has to be non-expensive, because the argument is kind of, okay, if it would not be non-expensive, your transport company would not, you would not give this to the transport company because it would be more profitable to transport this yourself. Okay, so the question is, what is the price function? This is actually not so easy to see typically what the price function is, but here actually you can figure out the price at location A should be 0, at location B 1/2, and at C 1. And then if you compute what you get as money and what you pay and subtract the 2 numbers, you get surprisingly the same number, which is 3/4. And that's not so surprising because there's a duality result behind it that guarantees that you get the same thing. This is the Kantorovich-Rubinstein duality. So the Kantorovich-Rubinstein duality basically says that you can either take the minimum of the best transport plan, where P is the transport plan that maps every pair to a probability distribution that maps every pair to a number saying how much you transport from one city to the next, says that the marginal distributions are the supply and the demand. And the other way is you go over all price functions, you find the best price function, and for each price function, you take the sum over what you pay minus the sum over what you get. Okay, and this is the same thing in this specific case. Okay, so now this was the motivation. So it's now half of the talk is over roughly. And now we come to how to generalize this. I mean, what is now the theory behind this, or which kind of theory can you do? So we want, so the idea is actually to model all kinds of transition system with various branching types. So not just, okay, now we do it for probabilistic, and then we do it for non-deterministic branching, and then we do it for other branching, everything at the same time. how do we get the fixed point equations in the general case? And are there some generic and efficient methods to compute metrics? Because in the end, I'm interested how to compute things, how to actually get the behavioral distances. And so the idea is here to use Coalgebra. This is a general categorical theory of behavioral equivalences. You might already know this. And so Coalgebra offers us a toolbox from which we can assemble transition systems of various different branching types and construct them, and then also analyze them with generic methods. In my case, analyzing means I want to compute these behavioral metrics, behavioral distances. Coalgebra is always based on a functor, so I'm just using set functors here, so set endofunctors. And so the ones I'm particularly interested in is power set functor. Let's just stay with finite power set functor, but you can, of course, also more general. Probability distribution functor, so finitely or countably supported probability distributions. Product functor, product with a fixed set. Coproduct functor, that can be used well for having maybe at some termination or some exception handling, and all kinds of combination of these functors. I mean, in principle, whatever you want, but these are somehow interesting functors in this context. And the functor defines the branching type of the transition system. So if you have a power set functor, you describe non-deterministic branching. If you have a probability distribution functor, you describe probabilistic branching. Product functor labeling and coproduct functor, I already said, it's like termination, exception, or failures that can be described this way. So then we fix a functor for our branching. And a coalgebra is just, since we're working, it's just in set. It's just a function from a set x to fx. Of course, you can consider coalgebras in other categories. It makes sense. But here, I'm just doing set for now. And so how do we instantiate these systems we've seen? Well, the metric transition system now is a mapping from a state space X to M, which is this fixed metric space from which we were taking the labels, times power set of X. And that's, so to each state, we assign a label and a set of successor states. And for a probabilistic transition system is of the type that for each state in X, you assign to it either a probability distribution over X, if it's not terminal, or it's a terminal state, and then you assign the singleton element to it. So, and that's just two examples. There are many different transition systems that you can represent in this way.
Barbara,
and sorry?
Can I ask a question?
Sure, of course.
The gamma, given a state x, for the metric, you get a number, you get a distance, m? No,
Yeah,
you get a point in that m. I see, you get a point
I get
in
an
m.
element of the metric space.
Yeah,
but
okay.
In the example,
you just label where you are. Okay, got it.
Sorry?
It's like at any state x, you know where you are and you know your next possibilities.
Yes, although I'm not sure this is where you are. It's more like what you emit, or how, I mean, what maybe where your color is.
Your observable, what you observably emit.
Or output is, or something like that.
Okay,
yeah, that's
thanks.
kind of your output towards the environment, and these are your successor states. Yeah.
Got it. Thank you.
Okay, so yeah, please feel free to ask if something is unclear. Okay, so now these are the coalgebras. Now, how to turn all this into a categorical framework with which we can handle all these behavioral metrics things. Okay, so first we're just taking a set coalgebra, standard set coalgebra. Now the next step is actually this. For the functor, we need a lifting. And the lifting is actually, we lift set functors to categories of pseudometric spaces. So category of the objects are the pseudometric spaces, and the arrows are the non-expansive function. And we fix some kind of lifting. So of course, I mean, you can view this as a fibration. So basically, you have set, and then you get this extra information, which is a metric on your state space, and the forgetful functor that forgets about the metric is just the fibration. And now the interesting thing is you have a functor on the base category, and you want to lift it to the upstairs category. Now assume just we're given some lifting. And once we have some lifting, then we can actually define what it means to get the behavioral metric. Well, you start with a metric on your state space, you lift it, you get a metric on fx, like metric on sets of states, metric on probability distribution over states, and then you reindex in the sense of the vibration with your coalgebra, because reindexing your coalgebra will get you back to a metric on x. So meaning you're reindexing for the metric means you compose with gamma times gamma. And this is a map from here to here. If you set it up correctly, it's a monotone map, and we also have a lattice structure here. So you just take the least fixed point of this map in the lattice of metrics or pseudometrics. And so this is just what it means to have a behavioral metric. You set up this map and you take its least fixed point. So what is a bit unclear maybe here is how do you lift the functor? I mean, you can just stop here and say, oh, I lift the functor somehow and that's it. But we were kind of interested in some more concrete ways to lift functors to pseudometric spaces. And so that for that we looked at these liftings that are known, especially this Wasserstein and Kantorovich lifting. For the distribution case. And we thought, okay, how can we generalize this? Is there a way to look at this from a more categorical point of view? And in fact, yeah, you can generalize it. There are now many variations on how to best express this. I'll just give you my view on this thing. So you need one parameter, and the parameter is an algebra. So it's an algebra on your truth value object. So the truth value object here is, for me, the interval 0, 1. You can do this more general if you want. So you take this algebra that tells you if I apply f to my truth value object, how do I get back to my truth value object? So that's what I fix. Once you have this, you fix a predicate lifting, because when you have a real valued predicate, meaning something that maps elements of x to numbers, you can apply the functor, compose with your algebra or evaluation map, and I get something that maps elements of fx to my truth value object, 2, 0, 1. And you can also do this with sets of evaluation maps. For the Wasserstein lifting, there you need some requirements, otherwise you will not end up with a metric, but I'll skip a bit over these fine points. So then there's a way to do the Wasserstein lifting more, let's say, categorically. So we call this Wasserstein lifting because in the literature very often this is called Wasserstein lifting, although actually there different names are used, but we had to fix something. And so you take a pseudometric and you take two elements of fx, and in the end you want to know what is their distance of the two elements of fx when you lift this metric d. And what you do is, well, you take all transport plans. So transport plans are now elements of f applied to x times x, whose marginals are the original element. Are marginals meaning you apply the functor to the projections, you apply this to t, you get these things. And now this here is something to which you can apply fd, so the metric living under the functor, and then you get something in f of 0, 1, and you evaluate. And you take the inf overall transport plans, the best transport plan. And this is a bit more diagrammatically, so you start with a d of this type. This is what you want to get. You take, for all transport plans, you apply this function. And, well, here you take the minimum over all transport plans with the corresponding marginals. You can also view this as a direct image in the vibration if you want. And so we view D as the real valid predicate lifting, a real valid predicate, we lift it, and then we minimize overall transport plans. Okay. Does it make sense? Yeah, it makes sense. Under the right conditions, this will also still result in a pseudometric, and it will also be it's also functorial. And then the Kantorovich lifting, you can do kind of the same thing, but now, of course, you generalize in a different way. So you take all non-expansive functions. That's the same thing as before. And for each non-expansive function, it's a predicate, a real valid predicate. You predicate lift it. So you get two lifted predicate. You apply this to the parameters, and then you just take the distance in this space 0, 1, which is just the absolute value of the differences. Okay, so this is also a generalization of the other lifting. Now, in the distribution case, they do coincide. Now we ask ourselves, do they also coincide in general? And well, we have some results. So both are pseudometrics under some constraints. This is also functorial, what we're doing. The Kantorovich lifting is always smaller equal than the Wasserstein lifting, but there are cases where they are unequal. You don't get the same thing. In many cases, you get the same thing, also for the power set factor, for instance, with the right evaluation map, but not always. And so it's actually an open question to characterize those functors and those algebras for which this works. This is actually a really interesting. I know many people are interested in this, but not so much progress has been made there. So non-expansive function isometries are preserved by the lifting, otherwise would not be a proper functor. And the Wasserstein lifting also preserves metrics. And so what do you get? So, I mean, you'll have to make two choices, a functor and an evaluation map. If you take, for instance, power set functor evaluation map max or inf, you get Hausdorff lifting. Distribution functor evaluation map expectation is Kantorovich lifting. Disjoint, coproduct, disjoint union, you take a standard distance on the disjoint union. For the cross product, actually, there are two useful choices for the evaluation function. It could be max or sum, and then you get also two interesting distances on the product. Or you can also, I mean, for the last two cases, you should do a bifunctor lifting, which I did not spell out, but that works as well. Okay, so you get some nice things, what you expect more or less, what you want. And so then, of course, that's already a theory with which you can work, and you can define behavioral metrics, you can find methods to compute them, and so on. So that's kind of the basic things. Now we'll go a bit more into compositionality and how to obtain witnesses. But if there are any questions right now, I'm happy to answer anything you might want to ask. Okay, so next question. Is this compositional? Meaning I have two functors and I've either lift their composition or I lift them separately and then compose them. Do I get the same thing? No, not in general. I mean, for the Wasserstein lifting, you have one inequality that always holds. And we have characterized some cases where the other also holds. So there's a notion of canonical lifting for which the other inequality also holds. For the Kantorovich lifting, it's the other inequality that holds. And if F is polynomial and you choose specific evaluation maps, you can also show that the other side holds. This is interesting because for some things we need, which I will show you now in a minute, we need compositionality. It's super helpful to have compositionality, but unfortunately you have to work to get it. You don't get it for free. So why is it useful? Because if you have compositionality, you can define up to techniques that help to define co-inductive proofs. So let me maybe say a bit what I mean by that. So in the end, we want to compute the least fixed point of a monotone function. And well, it's a monotone function on a complete lattice, so we're very easy settings. So it has a least fixed point that coincides with the least prefixed point and a greatest fixed point that coincides with the greatest postfixed point. So there's actually a proof rule. This is the proof rule here on the left that says, oh, okay, I just want to check whether mu f, least fixed point, which is my behavioral metric, this is by definition the least fixed point, is bounded from above by some given distance d. I want to check whether d is an upper bound for my behavioral metric. That's always a useful thing to do when you want to verify your system. So what do you do? I mean, the first attempt is to say, okay, let's check whether d is a prefix point, because if d is a prefix point, can show the upper thing, then the lower part, I get this automatically. This is just a consequence of cluster tasking. That's good. But people figured out that there's an even better way to do this. And the better way is to define another function u and to show this thing. And typically, u is supposed, at least in this setting, to make d smaller so that it is kind of easier to show this inequality. And of course, this doesn't work for all functions, u, but it works for functions that have some compatibility property. So UF is more UF and FU have to be related by an inequality. But once you have such an up to function, people found out that it's often much easier to show this and still get the same result, and they get this at a lower price. And okay, so now we want to do everything to this Coalgebraic categorical setting. And there's actually a theory of up to techniques. So now this is not our result. This is from the work by Filippo Bonchi and others, and they generalized this notion of up to techniques to this setting. And then I will tell you how we are then using it for behavioral metrics. So the first thing is that this up to techniques very often is it requires some operators on your state space. So it's basically it's up to some operators that you can use, or up to some contextual closure, or up to something that you do with your states. So you first need operators on your state space just to state your up to techniques. So you consider two functors actually. The first one is the same as before. This is what you get as branching type. And there's a distributive law that swaps this functor. And the T's actually must be a monad. So you have a monadic structure. And then in addition to your coalgebra, you get an algebra that's going from Tx to X. And that's the operator that stands for the operators that you have on your state space. And the algebra has to interact nicely with the coalgebra. So this diagram has to commute, and then it is called a bi-algebra. So you have a coalgebra, you have both something that has transitions, but at the same time, it has an algebraic structure, and these two structures interact nicely. So very often you get these by starting with a coalgebra of this form, and then using a so-called determinization construction, and then you end up with a bi-algebra with this state space. This is the typical way you get these bi-algebras. So okay, now assume we have a bi-algebra equipped with also such a distributive law. So we have an algebra and a coalgebra both on the same state space. We have a way of lifting functors, both the functor f and the monad that we're considering in the pseudometric spaces. And then actually we get such an up to function that can help us with these co-inductive proofs. And we do it by, okay, we'll start with the metric. It's again defined on metrics. I mean, because our fixed point equations are on metrics. Well, you apply the lifted monad T, you get a pseudometric on Tx. So this is kind of written in a fibration style. You work on the fibers above the respective sets. And then you do a direct image. So basically a direct image means you take two elements here, you take all their pre-images, and you take the minimal distance here. So it's a direct image which is adjoined to the reindexing. And what you get is typically some form of metric congruence closure with respect to the operators of the algebra. Okay, so now the question is, when is this a good up to function? So being a good up to function means this right-hand side proof rule has to hold. It does not hold always, of course. And the actually idea is that you have to be able to extend your distributive law to a distributive law of this type in your upstairs category. You easily get a distributive law on TF bar, so TF lifted to FT lifted, but this is not what you want. You want it to F lifted, T lifted to T lifted, F lifted to F lifted, T lifted. That's where you want. And once, so basically what you need to show is that these are, that the components here are non-expansive maps, then this proof rule holds. And that showing that these are non-expansive maps, compositionality helps you quite a lot, because you get this lifting with bar over everything kind of for free. And then using compositionality, you can argue that everything holds.
Barbara, you asked me to interrupt when you had about 5 minutes left. So
yes, okay, right. I'm also kind of looking at my watch. So I'll wrap it up in 5 minutes. I think that should be doable. You can then use this as a proof technique. And so this basically falls out of this general Coalgebraic categorical framework that now you can do this. And this has actually very nice consequences. So we were actually quite happy to see to now instantiate this to a real system, because you can actually really argue that this helps. It really gives you a very, very concrete benefit that you can now rely on this proof technique. And the example that we have it's quite small. So you have two systems. So there are actually systems that have both a label transition plus probabilistic branching. So assume you're in state X, you can do label A. Actually, there's only one label, so it's just a probabilistic system. And with probability 1/2, you get up here. With probability 1/2, you get up here. And each state is also labeled with some kind of payoff that's similar to the metric transition system. So it combines features of most of the transition system that we've seen so far. And here we have a state Y with payoff 1/2. You do an A with probability 1/2, you're back. And you want to know what is the trace distance actually between these two states. And the trace distance, I mean, it's there's also more concrete definition. Basically, you take all traces that you can do, and this because just traces are repetitions of A, and you compute the expected payoff that you'll get after an A. For instance, here, if you do an A, so you always get payoff 1/2. But here, actually, you might get a higher payoff if you end up in this state. So these are the payoffs, and you take the distances of the various payoffs, and then they take the maximum, the sup over all these distances. And so you take the sup of the distance of the payoffs. This is actually here now, we take truncated subtraction. So it's a directed distance. I'm kind of without really switching to directed distances here. And we could also define distances between probability distributions of states. Now our aim is to show that the distance is actually below 1/2. And we want to do this with these up-to techniques. So let's first do what you have to do when you don't do up-to techniques. You do it standard. When you don't use up-to techniques, you have to determinize the state space. And determinizing in this case means that you actually, in particular here, you now have a transition system where the states are probability distributions. So from this state, you go to this state and to this state, and then you see this is an infinite transition system. So now I have to define a metric on an infinite transition system. So I have an infinite object, and this is where computer scientists start to get super nervous, because I can't easily represent an infinite thing in my computer. So this is not what we want. So doing this the direct way, this would be just if you just take this one prefix point characterization. This is not the way to go. But you can use the up-to technique. So you just say, oh, I'm not interested in the whole state space. I'm just defining this for the distance between the probability distribution X and Y. These are just the Dirac distributions. Okay. And these are between the X prime and Y. I say both the distance are 1/2. This is my witness that I fix. And now I show that it is a prefix point up to. So prefix point up to is I put it into my fixed point equation. Concretely means, okay, I do the distance of these. Where on my distance, I first apply the up to function, then f. You do a couple of computations. And here you have a slightly fishy looking inequality that says, well, the distance of 1/2 x plus 1/2 x prime and y, this is more or equal than, well, you just pull the probabilities outside and you just do this. And this is, can you do this? Is this allowed? It's needed to actually show that you have a prefix point. So you have to do this weird step. And is it allowed? Yes, it is allowed because the up-to technique works. You get it directly from the up-to technique. So because the up-to technique gives you a metric congruence closure, and from the metric congruence closure, you know that this metric actually satisfies these properties. So if you want to instantiate the general approach, now, I mean, I've showed you transition systems, but how does this look in categorical terms? The monad is distribution monad. The functor is, to each state you assign a number, and for its alphabet symbol a successor. The state space are the probability distributions over Q. Okay, I'm mixing again. So yeah, X is the state space and its probability distributions over some, yeah, more lower state space Q. The coalgebras are of this type. To each probability distribution, you assign a number, and for each element label, you get the successor probability distribution. The algebra is just the monad multiplication, so it flattens your probability distribution. Then there's a distributive law between these two functors, which is kind of what you expect. Then you lift the two functors. So in one case, this is just product metric. So you do all these typical, these lifting constructions that I showed you before. In one case, it's just product metric and you take the maximum, and the other you could take the Kantorovich metric. So all this is an instance of the framework. So it satisfies all the contributions. Then the behavioral distance function that falls out of this is exactly the behavioral distance function that people use and that used to compute behavioral metrics that they used before they knew coalgebras. So this is the standard way to do this. And the up-to function is the contextual closure for barycentric algebras, actually. And this gives you this inequality. So if you have this, you take the distance between two probability distributions, this satisfies this if your distance has this specific property. And that's closely related to work on Madare, Panangan, and Plotkin, who worked about this on this quantitative algebraic reasoning, worked this out for barycentric algebra, and they have similar, they get the same inequality, basically. And then, okay, we have, of course, to get all this, we have to show that the distributive law can be lifted. This is the requirement for all this to hold. And we showed actually this. So the result that we have says if f is a polynomial functor and t bar is the Kantorovich lifting, I mean, not just Kantorovich lifting, the distribution case, this general Kantorovich lifting, then actually this works all fine. So we automatically get compositionality results, and from the compositionality result, we get that this works good. And we have some additional results on Galois collection on compositionality. Okay, and that's actually my last slide. So thanks a lot for the attention, and yeah, I'm happy to take your questions.
Great, thank you, Barbara. Okay, so if anyone has a question, please press the react button and raise your hand, and I'll call on you. I had a brief question. Did you use the symmetry of the metric, or because for the Hausdorff distance, you can just take a non-symmetrized version?
Yes, yeah. So I have to say I did a bit of a switch in the middle of the talk. So I started with the symmetry condition that I showed you, because actually we did part of our results are on the symmetric version, but actually this paper that I showed to you at the end is actually for the directed version. And okay. So we're doing both, and of course you would like to do maybe both at the same time. And maybe there are a few holes to fill saying that, oh, this also holds for the directed case and this also holds for the symmetric case and so on. Yeah. But in principle, it works for both. You can do both versions.
Cool, thank you. Someone had a question, but they unraised their hand, so maybe I'll raise it again. But another question I had was, is the stuff on the comparison between the Kantorovich and the Wasserstein, is that those comparisons for various Fs written somewhere?
Well,
You
I
had this
mean, what is
inequality.
written
Yeah.
so that the inequality holds. Yeah. There's so we have a journal paper. It's actually already a bit older, from 2016, in LMCS Coalgebraic. It's called Coalgebraic Behavioural Metrics,
Okay.
and that shows, let's say, many of the more basic results that I had in the first part of the talk. There we showed these inequalities and so on, and we showed also that this duality holds for specific functors. I mean, for one functor, it was already clear, distribution functor with the right algebra. But for the higher power set, it was not so clear that it holds, but it's not so difficult to see. You can figure it out relatively easily that it holds. We also have a counterexample where the two liftings do not coincide. That's functor x times x with, I think, some or so.
Do you know the intuition?
The evaluation
Intuition?
method.
Is there intuition for when it holds, or
It's
what
a
makes
bit,
it hold?
yeah. That's really a bit the big question. Why is it? I mean, it's kind of surprising that it holds. I mean, first it held in one area, and then we translated it to something completely different. It still holds. So you might think, yeah, why not? Can you not maybe do a general argument why it holds? I'm not really able to say something. People, I mean, of course I looked at the proof of the original Kantorovich-Rubinstein duality that goes via augmenting paths. So you can also invoke duality for linear programs or so. And you try to generalize this, but somehow our power set behaves very differently than distribution functors. And the idea you have in one, you cannot really transfer to the other. So it's more like it's a more case-by-case basis for now, and checking anew. And now we found some other cases actually where it holds. That's we're currently working on. But it's more like, and for each of these cases, it's difficult to show. So it's really hard to show. You have to invoke a lot of results. So having this general result that says this coincides under this and these circumstances, that would cover a reasonable amount of cases, that would be super interesting. But I really don't know.
It's really interesting. No other hands yet. So are these less than or equal tos that you get for the Kantorovich and the Wasserstein, are those natural transformations more generally? Like if you didn't land in a quantale?
This here that where are we? Here. That this is stands for the Kantorovich and this stands for the Wasserstein, that they are related by the smaller equal, you mean?
Yeah, and that smaller equal is in
that's just in the
reals, right?
Yeah, that's just in the reals. It just means
the enriching space of the.
Yeah. That's just on the reals.
And so, yeah.
Not sure how to.
Would that, if you were enriching in something besides, Levier's monoidal category, the reals, would you get a natural transformation or would you get some kind of comparison?
That's a good question. That's a good question. So of course, I mean, this is in the reals. We can also do it for quantals, of course, but I mean, this is still a lattice. I mean, basically, people in these areas, typically when they say vibration, they say, okay, vibration, that is where you just have lattice values, basically. So very simple types of vibrations. And then, of course, you can ask yourself the question, but what if I have a more complicated vibration? Will I get something interesting or will I get something useful? Yeah. I think this is kind of still open. I don't think many people have worked on this. Of course, I mean, the motivation is such that it's hard to think of why is it useful to go to a more general setting there? Does this help you somewhere? That's not so clear to me. Yeah,
I
but
mean, sometimes it's easier to see what you need, what the real thing you're using is, I guess, in some sense. Yeah.
that you understand a bit better what is happening there. Yeah,
Yeah. What's particular about metric
yeah,
spaces versus would work in any setting.
yeah,
Yeah. Interesting.
yeah.
Well, why don't we end the talk there? And thank you again, Barbara. And we'll
Okay.
end the live stream. And sometimes, as I mentioned earlier, people stay on a bit for some more
Mhm.
questions.